Okay, now let's check the results. Now go to the results, right click on it. You'll be having the multiple plots here. Go to the first one, create model solution data report. Give rectangular plot. We have to take S parameter, S11. We have only one port, so this is showing only S11. Always S11 we have to measure in dB, right? So there are two important parameters. I'll give new report and I'll be discussing about this. Give new report. So the graph will be selected, right? Then close. So there are two important parameters to check the antenna. One is the return loss, which is going to give the reflection. Now let's see here. In the design, this return loss or reflection coefficient is obtained with respect to the port, so that it is given as S1, 1 with respect to the port. That we are ensuring that whether all the electromagnetic waves connected at the port are transmitted to the specified structure. When it is completely transferred to the specified structure, if you have any impedance mismatch, it will be reflected back. If your impedance is perfectly matched, that is the characteristic impedance of your structure is perfectly matched to the characteristic impedance of the port, then you will not have any reflections. So if there is no reflections, right, your reflection coefficient will be, if there is no reflections, the reflection coefficient will be nearer to 0, right? So that means uh, completely 100% is taken into a antenna, and no reflections have been taken place. Reflections coefficient will be completely 0, right? If there is a reflection, then your reflection coefficient will be 1. All the waves incident has reflected back. So reflection coefficient is reflected waves divided by incident waves. So that you will be getting it as completely 1, right? So when you are there is no reflection, you will be getting the S parameters as uh, very high value. That is high positive value. When there is no when there is no reflections, you will be getting it as a high negative value, because it is lesser than 0, right? So it's nearly 0. So logarithmic value of 0, because we are mentioning in dB, logarithmic value of 0 or 0 to 1 will be a negative value. You are multiplying it by 10 to say it is in dB, right? It's a power value. If it is a power value, multiply by 10. If it is a voltage value, multiply by 20 to convert it to the dB. Now we get the shape of the curve like this, and your maximum is at -5. We can place the marker, right click on it and go to the marker, give add marker. So you can show this tip value, it is around 4.98. So it's not lesser than 10. So you have some impedance mismatch. So it's not completely transmitted, right? So if you measure all the calculate the values of rectangle, the dimensions and other things, so then you will be getting it in a proper way, right? So now we have given the center frequency as 3, but it is now shifted nearer to the 3.5, and we are not getting the mismatch, perfect impedance also. So the antenna is not working perfectly. But I'll show you how to check the results. The next important result is gain. So again, click on the results, create far fields report, right? Again, you have to always measure at the far fields, not in the nearer field. So go to the far fields report and connect it as the radiation pattern. So in the radiation pattern, gain, total gain, again gain is also measured in dB. Go to the second tab, families. Here you have given pi as all, and for 3 gigahertz frequency you have to measure, right? But we didn't get anything at the 3 gigahertz frequency, so you can select some other value, but we have created only for 3 gigahertz. We have given the simulation only for 3 gigahertz. Now give the pi value as 0 degree, right? It's not for all values. Go to 0 degree and select pi as 0 degree, right? New report. Okay. Theta value already we set it as minus 180 to plus 180. Let's check again. Um, Infinite sphere 1 minus 180 to plus 180 theta. Okay, let's check this one. Okay, let us introduce. Okay, here the geometry is infinite sphere. Okay, so from complete 0 to minus 180 to 180, you get this one. This is only for theta value we have set. And we can also draw the azimuth angle pi. For that, modify report. Again, take the same thing, gain, total gain, and dB, but give the primary sweep as pi. And go to the families and give theta as 0 degree. Add a trace. So you are going to add this as an additional curve in this. So give add a trace. So this is your azimuth plane radiation pattern, and this is your elevation plane radiation pattern. So both we have seen here. Here also you can add a marker to read the top value. What's the gain? Gain we get nearer to 2 dB. 2 dB magnitude we get. Right. And another thing what we can see here is results. Create far fields report. Go to the 3D radiation pattern. Create far fields report. 3D polar plot. Again, same thing, gain in dB. New report. So this is how your radiation will be. So you are getting the radiation in this way, but it is not perfectly matched. You will get nearer to 5 values. So some of the waveforms are getting reflected back. So you get the very less gain as 2.1. So if you get the complete radiation, you will be getting it as more than this. Around 3 dB, you will get the waveform gain, right? That's all the important things what we have to verify as a result, right? Please note down the steps, and we will be seeing the similar kind of simulations in your microwave lab. Thank you all.